So, today's class we will be concentrating on a new topic, a very interesting topic. It's called vector space of random variables. In fact, this is a huge topic and can't be covered just in one lecture. So, we will not make any attempt for that. But before I go into that, let us just go back to what we were discussing last time, because little bit of that was left. Last time I said that if to x and y are statistically independent, then Exy is nothing but Ex Ey. This leads to the fact that covariance C or correlation coefficient, which is C by sigma S sigma y, that is equal to 0. So, if they are statistically independent, this is always true. Okay, that is trivially seen. But if this is given, that is x and y are two random variables which are uncorrelated, then it does not necessarily mean that x and y are also statistically independent. That is, joint density of x and y, p x y, is not in general a product of p of x and p of y. Okay. But for a particular class of random variables, mostly actually the Gaussian random variables, that is when x and y are mutually jointly Gaussian, then statistical independence means uncorrelatedness as before, but also uncorrelatedness means statistical independence, that we can see. So, that works for Gaussian random variables. So, that means suppose jointly Gaussian, or sometimes we call jointly normal. Okay. Then we know what is the probability density. What is the probability density? Just a minute. This thing times exponential minus 1 by now, we have seen earlier, in fact, we have proved that this R is nothing but the correlation coefficient. So, suppose it is given that x and y are uncorrelated. In that case, R is 0. So, if R is 0, this term is 0, 1 minus R square means 1, so which is nothing but, so this becomes nothing but minus 1 by 2, and then x square by sigma r square plus y square by sigma 2 square, and this simply becomes 1 by 2 pi sigma 1 sigma 2, right. So, for R equal to 0, this leads to a very simple thing. We can write it as a product. One of them is root 2 pi sigma 1 e to the power minus x square by twice sigma 1 square, and again 1 by root 2 pi sigma 2 e to the power minus y square by twice sigma 2 square. So, this is p x, this is p y, which means the joint density is nothing but the probability density of x multiplied by the probability density of y, that is x and y are statistically independent. So, you see, as I said, that if x and y are statistically independent, they are always uncorrelated, that is true in all cases. But if x and y are given to be jointly Gaussian or jointly normal, that is equivalent way of saying, then if they are uncorrelated, then again the reverse is true, that is they are statistically independent too, but that is not true for other cases. So, it is not true in general, but in the case of Gaussian random variables, statistical independence leads to uncorrelatedness and uncorrelatedness leads to statistical independence. Okay. Okay. Now, we come to this important topic called vector space, rather Hilbert space of random variables, and this cannot be covered just in one lecture, because this topic of vector space as such is a semester long topic. So, I will not try, but I will just tell you the motivation. Actually, the random variables can be treated equivalently as though they are some vectors in some infinite dimensional world. See, we are all familiar with 3-dimensional world, which is spanned by 3 axes, x, y, z. We know that they are orthogonal, but they need not be orthogonal. The angle between them could be anything, but 3 mutually independent axes are required, and they span the entire 3-dimensional world. Any vector can be written as a linear combination of those 3 basis vectors or elementary vectors, one in x direction, another in y direction, another in z direction, right. So, we are familiar with this. Okay, we are familiar with other notions which are valid there also, like the dot product involving 2 vectors and all that. Okay. But this whole idea of vector space, this 3-dimensional vector world can be generalized to an arbitrary n-dimensional and later infinite dimensional vector space, where you do not have any notion of these physical vectors, the position vectors, which we are familiar with in the 3-dimensional world. Okay. But there all the advantages that we are, or all the results that we are familiar with in the conventional 3-dimensional vector space, they are all present there. Okay. So, in a vector space actually, and we are defining vector space, we are using vector space over the field of we say over the field of complex or real numbers. Maybe in our case, to make life simple, we are taking vector space over real numbers, means whenever we come across any scalars and any number, we will assume that number is just nothing but a real number, and we all know all the operations on real numbers, how to add to real numbers, how to subtract and all that. So, I will simply consider the vector space of random variables, okay, over the field of real numbers. That is, let H be set of all possible, maybe 0 mean, to make again life simple, random variables. Okay. Now, this is just a set, it does not become a space. Here every random variable will be called a vector. Every x element of H a vector. Please do not confuse this vector with your traditional, your conventional, notion of vector. There is a column vector, row vector, or position vector, not at all. This term vector is just an abstract term, it is an element, you can call it an element, but we call it vector because there is an analogy between these treatment and the 3-dimensional vector world. That is why you say it is a vector, but actually it is a random variable. There is nothing vector like about it. See, x is just a random variable, it is not a column vector or row vector or a position vector, it is just a random variable, but we just call it that it is a vector. So, that is in an abstract sense. Okay. It becomes a vector space H under certain conditions. What are the conditions? That if you take any vector y x and any other vector y, that is 2 random variables x and y out of H, there must be a rule of addition of these 2 vectors, so that you get another random variable. So, there must be some rule of addition, so that x and y can be added and you get another element which must also belong to H. First, let us see what can be such rule of addition, and under that rule of addition, if you really add x and y, do we get something which should belong to H? Let us first verify that. When I say x plus y, it means every time I conduct this experiment on x and y jointly, I measure the value of x and simultaneously measure the value of y, whatever the values come up, in those cases I just add them up. So, I get a resulting value. Obviously, this resulting value changes from experiment to experiment. Okay, so, resulting value corresponds to a random variable, and that random variable is z. That means, every time the value of z is obtained by summing the particular value of x and particular value of y that have come up in that experiment. That is the meaning of this random variable, the addition of 2 vectors. In fact, that is how we add to random variables also, there is a usual meaning. Okay. But since the resulting variable, resulting quantity is a random variable and H consists of all possible random variables in the world, z also belongs to H, z does not go somewhere else. So, we say that it is closed under this vector addition. This addition should satisfy some basic properties in order for this H to become a vector space. One of them is that this should be commutative, which is obvious because you will be adding the numerical values for x and y to get the resulting values. So, it does not matter whether you add the value of x with y or value of y with x. Then now we take z to be some other random variable. So, x plus y plus z, it should be same as this is called associativity. Then in this set there must be a unique 0 vector or 0 element or 0 vector. What is the 0 vector? That is, it must be a random variable, so that for all x element of H, x plus 0, that is, if you add the random variable x with this particular random variable called 0 vector, you should get back x. This 0 vector is what? Is also a random variable, but it is a random variable which in all experiments takes only 0 value. We say using probabilistic language, it is a random variable which takes the value 0 with probability 1. Obviously, whenever you conduct experiment on x and simultaneously on this random variable, you get some value of x, but 0 value always from this. So, that value of x plus 0 will give you the or return you the value of x only. So, that is why this equality is satisfied. So, this H consists of one such random variable called 0 random variable. So, this is also satisfied. And finally, for all x element of H, for each x there exists a negative of that element of H. What is meant by that? So, that when you add x to this particular random variable, this particular vector, this is a notation minus x together, I say that is a vector, and when x and minus x these two are added, this should be this 0 vector. So, for each x I should have one such vector, so that when these two are added you get 0 vector. Now, does it exist here? Answer is yes. If there is a random variable x, I can always define a so called negative version of it, may be denoted by this. How? Whatever value of x I obtain by an experiment, I will take the negative of that, assign that value to this random variable minus x. So, whatever I add x and minus x, the two values cancel each other. So, you get a 0 value. So, resulting random variable always takes 0 value or takes 0 value with probability 1. So, it must be this 0 vector, right. So, these are the basic things that should be satisfied, and they are indeed satisfied. Okay. That is relevant to this addition of two components, any two elements of H, or these elements are also called vectors. Though again I repeat, there is nothing vector like, nothing column vector or row vector like or position vector like. The vector is a just term here. Okay. So, here these rules are in the context of the vector addition. That is one side of the story. There is another operation. One operation is that H has a rule of vector addition involving the vectors or random variables, but whenever you add two random variables, the resulting vector or resulting random variable also should belong to H, and that is indeed the case. Okay. The other operation is scalar multiplication. That is, for any x element of H, and take a scalar C element of real number. So, C is just a real number, R is the set of all real numbers. First, Cx, when I write Cx, I mean I denote by this abstract notation Cx another random variable which must also belong to H. It should satisfy some basic property. Now, how we get this, how we form this Cx in practice? I observe x in an experiment, whatever value I get, multiply that by C. So, I get another value, but that value also is random, because every time I measure x, I get new and new values of x. So, Cx also takes new and new values. So, this resulting thing also is a random variable, Okay, so Cx then belongs to H, but this Cx, I mean, in the general case, not necessarily in the case of your this particular vector space of random variables, in the general case, it means that for any vector which is belonging to this vector space H, and for giving any scalar C, Cx should denote a new vector, but it must also belong to H. We call this new vector as the scalar multiple of x, but the scalar multiple of x must satisfy some basic properties. One, if you have things like this C1, C2, if you break C as C1, C2 x, you can as well have C1 followed by C2x. That is, take x, multiply by scalar C2, you get a new vector. On that again, multiply that again, you multiply by C1, so you get another vector. That should be same as taking x, multiplying by this C. Okay, this should be satisfied. Then other things also are very simple. This should be this. On the other hand, for any x y, this is trivially satisfied, because in our all experiments you observe a value of x multiplied by this summation C1 plus C2, whatever you get, you will get the same thing if you multiply the value of x by C1 and by C2 and add those values. Similarly here, if you conduct a joint experiment on x and y, add their values in any experiment, multiply by the C, you will get the same one if you take the individual value of x, individual value for x multiplied by C, individual value for y multiplied by C and add them. This should be satisfied, and obviously this is satisfied. These basic conditions should be satisfied for any space to be vector space, and we are seeing that these are satisfied for our H, where H is a set of all possible random variables. And 1 x, if you take any vector x and take a scalar 1 and consider the scalar multiple of x by 1, this is again another vector, this should give you back x. And obviously this is satisfied again for H, because when you have an experiment on x, whatever value you observe multiplied by 1, you get the same value which you had for x. Okay, so they are satisfied. So these basic conditions are satisfied, means H is a vector space. Okay. In this case, like we had suppose there is one vector p, another q, and I say this whole two dimensional world is spanned by p q, means you consider any point x, any point, this will be some linear combination of p and some linear combination of q, I mean some linear combination of p and q. Okay, so every point of this space is a linear combination of p and q. P and q, they are linearly independent, because q cannot be expressed in terms of p, this is pointing in this direction, this is pointing in this direction. Similarly, p cannot be described in terms of q, we say they are linearly independent. Okay. In general, if you if you have more than two dimensions, say another dimension, p, q and maybe r pointing upward, okay, R, p and q again they form a linearly independent set, because r cannot be expressed as a linear combination of p and q, because any linear combination of p and q will be in this plane where r is pointing upward. Similarly, q cannot be expressed as a linear combination of p and r, and p cannot be expressed as a linear combination of q and r. So they are linearly independent at any point. And what is meant by span of them? Span of them means set of all possible linear combinations of these. For instance, span of p and q means you take all possible linear combinations of p and q. Linear combination is typically of the form some C1 times p plus C2 times q, where C1 and C2 two scalars. Plug in any value for C1, any value of C2, you get one particular point, and go on, go on. So this 2D world is nothing but a set of all possible linear combinations of p and q. That we will be calling, we will be saying is a span of p and q, okay, and here p and q are linearly independent. So then p and q will be called a basis of this entire two dimensional world. Similarly, if it is three dimensional with a vector r pointing out, p q r form a linearly independent set. What is the span of p and q, p q r? It is a set of all possible linear combinations of p q r. typical linear combinations of this form C1p plus C2q plus C3r, which is a vector pointing in the space, and you plug in any value of C1, any value of C2, any value of C3, you get some particular point in the 3D space. So, basically span of PQR means, collection of all points in the space means the whole 3-dimensional space. Okay, and PQR becomes a basis because they are linearly independent. There is no redundancy there. Every vector is needed. P is needed, Q is needed, R is needed. None of them can be expressed as a linear combination of the rest. Everybody is required. Okay. Similarly, here also, if you have some vectors x1 to xp, they are linearly independent if none of them is expressible as a linear combination of the rest. So, x1 should not be expressible as a linear combination of x2, x3 up to xp. Same for x2, x2 should not be expressible as a linear combination of x1, x3, x4 up to xp, and so on and so forth. In that case, this becomes a basis of W, which is a span of means set of all possible you can see one thing. If we just take p elements x1 to xp, consider all possible linear combinations of them and form a set. My claim is that set itself becomes a vector space. We call it a subspace because there is a subset of the mother H. How would you say that this becomes a vector space? Well, you take one combination, that is one element of the span. Take another linear combination of these two, that is again an element of the span. You add them. So, earlier maybe you had C1 x1 plus C2 x2 plus dot dot plus Cp xp, that is one element of W. Now, you have got D1 x1 plus D2 x2 plus dot 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 dp xp, that is another element of W. If you add them, you have within bracket C1 plus D1 times x1 plus C2 plus D2 times x2 plus dot 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 dot, which is again another linear combination of these elements. So, which must also belong to W because I am considering set of all possible linear combinations, right. And you can see that if you take any linear combination, if you take all the coefficients to be 0, okay, then obviously you get 0 vector. So, 0 vector is present for any vector, any linear combination. If you reverse the sign of the coefficients, if it is C1 make it minus C1, if it is C2 make it minus C2, obviously you get negative of the previous combination. So, negative of a vector also is present, and likewise you can verify that all those basic axioms of a vector space are satisfied by this set of all possible linear combinations of these. And if they are linearly independent, then I say that this becomes a basis. Linearly independent means none of them is expressible as a linear combination of the rest. Okay. Now, I am trying to do things fast and I am skipping many mathematical details. Now, you know that in a 3-dimensional world there is something more that you are familiar with, that is a dot product involving two vectors. What does the dot product give you? It takes two vectors and gives you a real number. How? If the one vector is p, another vector is q, then p dot q is nothing but length of p times length of q times cosine theta, where theta is the angle between p and q. Okay. That is, if it is theta, then p dot q is nothing but length of p, length of q times cosine theta. Now, when you deal with a general vector space or the vector space of all possible random variables, obviously we do not have any angle there, because the angle is a physical, is a parameter which occurs in the positional world, in the 3-dimensional positional world. But we are now dealing with a vector space of random variables, there is no such angle occurs, right. But this dot product actually in our language is called inner product, and this inner product just should satisfy some basic properties, a definition of inner product. So, depending on the context you can throw your own definition of inner product. It should satisfy some basic properties, those are independent of these physical parameters like angle and all that. If those basic properties are satisfied, then we can live happily with this. That is what mathematicians found out. In the case of 3-dimensional world, this was defined to be the inner product, and this was satisfying also those basic axioms, and people could live happily with this. Those axioms are like this: inner product, instead of calling it x dot y like p dot q, we say x comma y bracket. It takes x and y, where x and y are two random variables, that is for all x y belonging to H. What does it do? It gives you a real number because we are considering a real number case. Okay. But it satisfies some basic properties. It should satisfy some basic property. If your definition of the inner product satisfies those, this will be acceptable. Like this definition was acceptable in the 3-dimensional vector space, positional vector space. Those properties are simply that instead of the vector x, if you have a combination here x1 plus x2 comma y, you should be able to. So, that is, instead of having just one vector, you have x1 plus x2. So, first you take x1, x2, form their addition. So, this is another vector of H. That vector comma y, its inner product is a real number. This will be same as if you take the inner product of x1 with y and x2 with y. You see, this is satisfied here. If you have P1 plus P2 dot q, you can see geometrically P1 and P2, this could be P1, this could be P2. So, P1 plus P2 will be this vector. You can see that dot q is nothing but P1 dot q plus P2 dot q. It can be proved easily, okay, using some geometry. So, this should be satisfied. Okay. Secondly, either product between x and y and x, this should be conjugate of each other. Why this is a complex number, but we are dealing with real case. So, for real number, conjugate has no meaning. So, for our case, x comma y and y comma x, they are same. For instance, p dot q and q dot p, they are same, because they are in this case also we are getting real numbers. But when we are dealing with complex valued case, x comma y inner product may not be a real number, may be a complex number, then y comma x, its conjugate should be equal to x comma y. Number 3, if instead of x you have a scalar multiple of x, like instead of p dot q, I have some c times p dot q, that should be same as taking c out. Here, like you can take c out, within bracket put p dot q, carry out this, then multiply this real number by c. Same thing should be valid here also. And last one is very important. If you take the inner product with itself, like p dot p, it is nothing but length p square, that is all, because theta is 0, cos 0 is 1, length p square, which is a real number always and always greater than or equal to 0. It is 0 only if p is a 0 vector. Similarly, here also inner product with itself, this is real greater than or equal to 0 if x is the 0 vector, because H, the vector space, has a 0 vector. So, if x is a 0 vector, then only the inner product of this with itself will become 0, otherwise it is a real positive quantity. This should be satisfied. Okay. In fact, inner product with itself, which is nothing but in the 3-dimensional case square of the length is also called norm of a vector. Norm is something similar to length, that is a real number, is denoted by this double line. So, this should be square of this length square. This norm of x is equivalent to the length, though there is no apparent length here for a random variable, but it is something equivalent, and square of that. This is okay. So, this should be 0 only if x is a 0 vector belonging to H. Now, for H, this is a very general definition. Okay, these are the conditions that inner product definition must satisfy. Now, in the case of H, I say that we can define an inner product like this. Right? We can define an inner product like this. That is the correlation. Take x, y, multiply, take expected value. Now, does it satisfy all the properties? Answer is yes. First, instead of x, if we have x1 plus x2 times y, this E is a linear operator we have seen, it becomes E of x1y plus E of x2y. So, this is satisfied. Similarly, E of xy or E of yx, they are one of the same, so satisfied. Similarly, E of cx times y, you can take c out because c is scalar and therefore non-random, it can go out of the expectation, and you have c times E xy. This is satisfied. And lastly, x comma x inner product with itself is nothing but E of x square, which is nothing but the expected power, okay, of this random variable, or even variance you can say, because the mean is 0, and this is always positive because x square and then expected value. This is always real and positive or greater non-negative, and it can be 0 only if x is such that it always takes 0 value. So, its square also is 0 value. So, if you take the expected value, that also is 0. That is, x is a 0 random variable which takes 0 value with probability 1. This is the correlation, right. Now, you have seen one thing previously, that we can write cos theta in the 3-dimensional world as, sorry, okay, and this is always less than or equal to 1. Our question is, do we have this thing valid? Is it so? Answer is yes. This is a famous inequality called Cauchy-Schwarz inequality. This will be satisfied. How? Let us see how. Take for any real, this is important, any, for any real number a, we can always say which is nothing but norm square of this must be greater than or equal to 0. Okay. In fact, when it is equal to 0, only if x and y are such random variables, so that we can find some scalar number a for which a times x is equal to y, then only it becomes 0. And as I told you earlier, norm square or norm can become equal to 0 only if we have a 0 vector here, and this can become a 0 vector only if y is such that it is some scalar multiple of x. So, this is equal to 0. but here we are writing in the using the general notations of inner product and norm. In our case, actually it becomes expected value of square. This we always know is greater than equal to 0. So, I am rewriting this using our definition of inner product, right. Now, equal to 0, here is greater than equal to 0. Equal to 0 means if and only if x, y are such that y is a scalar multiple of x. Okay. Suppose it is not. Suppose x, y is not a scalar multiple of x. Then let us see whether that is satisfied, whether the triangular inequality is satisfied. You see, when it is equal to 0, what happens then? After all, we are trying to find out, we are trying to prove that E x y, we are trying to prove that Cauchy-Schwarz inequality, right. We are trying to prove this quantity, this thing. We are trying to prove that E x y maybe you can take a square of it, because if it is less than equal to 1, square also is less than equal to 1. This is less than equal to 1. So, I have squared up, otherwise this square will not be here, it will be a square root, because square root E of x square is the norm of x, square root of E y square is the norm of y. So, norm of x, norm of y, and here is just inner product between x and y. But I wanted to get rid of the square root in the denominator, so I just squared up, because if before squaring up it is less than equal to 1, then after squaring up also it should be less than equal to 1. So, you have to prove this. Okay. Now, in the first case, when x and y are such that y is a scalar multiple of x, we are dealing with this case, this becomes equal to 0. Okay. What happens in that case to this ratio? You can see this ratio becomes equal to 1, because y square means a square x square, a square can go out. So, a square e x square e x square, and here a x square, a goes out, e x square, okay, and a whole square. So, a square and a square cancels, and e of x square is doubled because of the square. So, it cancels from numerator and denominator, so you get equal to 1. So, this quantity when equal to 0, which means when y is a scalar multiple of x, then we have this ratio equal to 1. Now, we consider the case where this is not satisfied, that is y is not a scalar multiple of 1, it is a multiple of x. In such case, this is strictly greater than 0, right. So, we are considering this case for any scalar ray, implies strictly greater than 0. Okay. We can write it like a square okay, call this quantity b square, this quantity c, and this quantity d square. So, a square b square minus 2ac plus d square greater than 0. You can write like this: ab minus, so this is ab whole square, so twice ab into c by b. So, you have to have the c by b whole, ab minus c by b whole square. So, c square plus b square was introduced. So, it has to be subtracted. So, plus d square minus c square by b square. Okay. This should be greater than 0 for any a, that is very important. Now, when is this is equal to 0? If a is c by b square. Now, c is this inner product or correlation, and b square means just the variance of x. Both are real numbers, they are given to us. So, I can always choose a to be a real number like this. For this choice, this quantity is 0, but even then this inequality must be satisfied. So, this must be greater than 0, because this is true for any a. So, this is true for this a also. For this a, this part is 0. So, this must be, this is a quantity which should always be greater than 0, right. Okay. What does that mean? That c square is less than b square d square, or if you take the positive square root from both sides, c must be less than b d. This implies what is c? C was, and what is b? Square root of positive square root. What is d? Again positive square root of this. You can square up both sides and you get your result. This is a famous inequality called Cauchy-Schwarz inequality. Okay. This treatment actually is very useful, this Hilbert-Street treatment, for carrying out estimation, okay, in using random variables. That is, some unknown random variable is to be estimated as a linear combination of some observables, some random variables which can be observed as an optimum linear combination. So, what could be that optimal linear combination? After a few lectures, we will consider mean square estimation. There we will see that such an optimal estimate as a linear combination of a few given random variables is nothing but something called orthogonal projection of that unknown vector into the space spanned by the given set of random variables. Okay. So, for that this is very important. Now, I tell you again that this whole vector space theory cannot be covered in one lecture. You know, for it to be mathematically accurate and rigorous, it needs several lectures. So, if you are interested to know more about it, more about vector space theory, you can consult any book, because there are plenty of books available on this, or maybe you can just consider this book. This book has several chapters, just consider the chapter on vector space by okay. Before I conclude, I will cover another one small topic. That is, suppose z is x plus y, x and y are two random variables, and z is another random variable obtained by summing x and y. X has mean mu x y has mean okay. So, what is the mean of z? Obviously, expected value of z is nothing but expected value of x plus y, and you can use the linearity of expectation operator. So, that is nothing but expected value of x plus expected value of y. So, obviously, mu z, which is nothing but E of z, is same as mu x plus mu y. That comes trivially. And what happens to the variance? Sigma z square, which is nothing but E of z minus mu z whole square. Now, this you can write as, you replace z by x plus y, mu z by mu x plus mu y. So, this becomes nothing but whole square, right. So, square of this expected value of that will give you the variance of x, square of this expected value of that will give you the variance of y, and then we have twice E of x minus mu x, y minus mu y, which is nothing but the covariance. Covariance either you can write by C, or you can write it as a product of correlation coefficient R times sigma x, sigma y. Okay, so, if R is given, sigma s is given, sigma is given, you can find out sigma z square. Okay. So, I will stop here today, but let me tell you, I mean in a nutshell what we are going to do soon. From here we will move to moments. Like you remember, in the case of single random variable, we defined moments, okay, and moments were used for what? I mean, we derived some properties of the moments, okay, and from moments we merge to characteristic functions. Here also we will merge to what is called joint characteristic function. But before going from moment to joint characteristic function, I will again come back to one topic which I had left out, thinking that I may not need it, but that topic I find also is important. That is the two functions of two random variables. So far I consider only one function of two random variables, that is g of x comma y, but I will be now considering two such functions. Maybe one is f of x comma y, you call it z, and another is g of x comma y, you can call it maybe v. So, there are two functions, and obviously z and v are in general jointly related. So, I have to find out the joint distribution function and joint density of z and y. Okay. So, that we will be doing in the next class. Thank you very much. Okay. So, today we discuss this first, and then we will go up to joint characteristic functions. Okay. We are given jointly random variable. Okay. Then we define the moment MKR as
where Pxy is the probability density of joint probability density of xy, okay, x to the power k, y to the power r, and this will be called joint moment of xy of order n is equal to k plus r. So, it is very much similar to the moment that we dealt with for a single random variable case. It is a generalization of that to two variables. Okay. Certain things follow easily. What is M10? That means x to the power 1, that is x, y to the power 0, that is 1, x, p x comma y dx dy. And p x comma y can be written as, that is p x comma y can be written as you can write the entire thing like this, x p x dx, p x comma y will be written like that is p x comma y is p x times p of y given x. So, this integral is 1 because condition to any x, total probability of y taking values within minus infinity infinity, that is equal to 1, and this is the mean value of x. So, M10 is mu x. Similarly, M01 will be mu y. Mu y means the mean of y. Okay. Then what is M11? Or say start with M20. Clearly it will be expected value of x square. Why? Y0 is 1, x square, p x comma y dx dy, p x comma y will be written as before like p of y by x, and then p x, this integral will be 1, and we get expected value of x square. Similarly, M02 is e of y square, and M11, that is expected value of xy. Okay, that is, these are all second order moments. Okay, second order joint moments. Similarly, you can have joint central moments. Here you can call it M prime K R. It is actually expected value of omega 1 x plus omega 2 y dx dy. So, given p of x comma y, or you can equivalently see also, there is nothing but expected value of e to the power j omega 1 x plus omega 2 y. Okay. So, given p x comma y, we can find out phi by this formula, and given the characteristic function, we can find out p of x comma y by the inverse formula. That is again obtained by just by recalling the forward and backward Fourier transform relations. So, that is direct and indirect, okay, inverse, direct and inverse Fourier transform relations. Okay. That is, you can see that if you multiply both sides by 1 by 4 pi square, then this is nothing but inverse Fourier transform. of px comma y at omega 1 comma omega 2. See, there is a plus sign here, no minus sign, no minus sign. We recall in the one variable case, the inverse relation was 1 by 2 pi integral some function of say x e to the power j positive e to the power plus j omega x dx. Here we just have two variables x comma y, so px comma y e to the power this, okay, 1 by 4 pi square. So this is again inverse Fourier transform of x comma y at omega 1 comma omega 2. So px comma y is nothing but direct Fourier transform of this quantity. Okay. That is px comma y px comma y is 1 by 4 pi square okay. So this is the definition, and for the given phi omega 1 omega 2 we can also find out the marginal characteristic functions, that is just phi of omega 1 and phi of omega 2, phi of omega 1 being the characteristic function of x, okay, for the random variable x alone, and phi of omega 2 being the characteristic function for the random variable y alone, okay. And then we will see that when two variables are independent, statistically independent, then this joint characteristic function becomes just a product of, if the joint characteristic functions is a product of two marginal characteristic functions, then x and y they are statistically independent, okay. And then we will relate that to convolution and all that. So that will be for the next class. So that's all for today. Thank you very much.